let's quickly go through the quiz. So this is examples of ways that I can ask you about naming or reasons why naming is important without just questions of what is this name, what is this name. If we're going to talk about chemicals, we have to know what we're talking about. So if a lab procedure or something asks for a certain amount of manganese nitrate, you need to know that the symbol for that molecule is MnNO32. Right? All right. Okay. So that affects the molar mass. So let's quickly look at that. So manganese is going to be about 55. Now we got 3 significant figures, so we should really use 3, and the molar mass is 2. But for speed, maybe a point if you do the rest of it right. Yeah, that's usually how I do it. So we've got 2 nitrogens and then 6 oxygens. All right, you add all that up and get whatever you get. And then to figure out the grams, you would say 11.0 grams times whatever this number is. Well, you didn't do it right, so I'm not trusting your number.
the last minute I took off the 2.
Oh, okay.
86.
So what did you say it was? 170?
179. Not to 86, to 128 or something like that. I was so mad.
All right, and whatever that is for moles. Okay, same idea for ammonium acetate. Formula for ammonium acetate is going to be NH4H3O2. Or C, another way that acetate is often written is CH3CO2 minus, or CH3COO. Yeah. As long as you got 2 carbons, 3 hydrogens, and 2 oxygens, you'll be good. So same idea here, just make sure to remember that you're in milligrams, not grams, when you do that conversions. So you can either keep it in milligrams and end up with millimoles, or you can convert it to grams and do the same thing, whatever that number is. Okay? Similar problem here, but now we're asking for molecules in a volume. So we still need to know the formula for antimony pentafluoride, which is SbF5. Right, SbF5. And antimony pentafluoride is actually a liquid at room temperature. So we do measure it in milliliters. And to measure the amount of a liquid in milliliters, but to know the moles or the molecules, you have to use the density. So we can set up a big string of these things again. We can say 2.50 ml times 2.99 grams per 1 ml, or cubic centimeter, that's the density. That's going to give us grams. Then to get moles, we're going to divide by the molar mass of antimony fluoride, whatever that is, antimony pentafluoride. Anybody know that offhand or calculate it? That's okay, we can, you know what it is. And then once we have moles, we know that there are always 6.02 times 10 to the 23rd molecules per 1 mole. Put all those together, and you get whatever you get. Big numbers. Okay, questions about those? Right, I think in all of these, if you got the name wrong but you did all the steps correctly, I'll take off a point or a half point or something. Or maybe I'll take off a point for the first one you get wrong, but then I won't take off any for the next one you get wrong. So it's not too bad.
Yeah.
Yeah. So we'll see. But these kinds of problems, from a conversion standpoint, these are pretty simple. The tricky part, of course, was the name for a lot of you. But please be working on this, because exam next week, this will certainly be a big part of it, as well as some more complicated conversion questions like you saw in Mastering Chemistry or in the homework that we haven't really had a chance to do on a quiz yet.
You said exam next week, right?
I think that's right, isn't it? Thursday, yeah. Valentine's Day. Happy Valentine's Day. It'll be like a special Valentine. Yeah. Actually, this happened last year, and I made the cover sheet of the exam like a Valentine thing. I think people really didn't like that. All right, so let's name these. This first one is tin 4 oxide. Was it close? Those of you who went, oh, are you close? All right, well, that's close. But remember, oxide is a 2- ion. So if there's 2 of them, it's got to be 4-. What about GAN? Gallium nitride. If you put the 3 here, I won't count it wrong. But gallium does generally just have the 1 oxidation state, so it's really not necessary. Okay. And then what about this one?
Chloric acid.
This would be chloric acid. And the last one? That's right, cesium telluride. I don't know if I want that sort of resolution on the screen. It gets a little complicated. If I wanted to give half points, I would just make them out of 20 instead of 10. But yeah, I mean, if you think about this, well, yeah, this is a little bit extreme for the quiz because each name was worth 1 point, whereas in an exam, a naming problem wouldn't be worth 10%, just the one name. So, you can afford to miss a couple on the exams. How many questions? I don't know. We'll see. It'll be a mix. This will be helpful for the lab today. We talked last time on Monday about balancing equations a little bit. Or we didn't talk about balancing equations. We talked about kind of chemical equations in general, right? And how they have to be balanced. Now a couple other pieces of those chemical equations. First of all, we also need to have the physical state of the molecule. We need to know what form it's in. You've probably seen these before. If not, you definitely will tomorrow. You guys spilling more water here? Everything okay? All right.
Water everywhere.
You got 4 possibilities: solid, liquid, gas, and aqueous, which is a solution of something. Right? So something dissolved in water. Those you'll also see in the chemical equations. And if you've been working on your Mastering Chemistry, I think 3B it is, or 4, it's important that you put those in as well in your equations. So that's what something might look like. Is this one balanced as it's written here? Maybe. Always a good.
Yeah, it is balanced.
Okay, yes, it is balanced. It is balanced. So this is something you want to keep going in your head, especially when we get to exams and finals and stuff like that. Always check equations. Whenever you see an equation, check to see if it's balanced or not. Because we won't always say in a question, make sure you balance this equation first, then solve this problem. It's assumed that you'll look at an equation, see if it needs to be balanced or not, and then do it. So anytime you look at a chemical equation, don't assume it's balanced. Do a quick check and see before you go on and do whatever problems you're going to do regarding that. All right? So here are some various steps. Everybody kind of seems to have their own method of doing this. I'm going to kind of show you how I do it. If you learn it a different way that works for you, that's totally fine. In all cases, there's a bit of trial and error involved in balancing equations. And that's fine. You can try stuff, erase it, whatever. Here are some examples that we're going to go through, and I'll help you out with a couple, and then you can do a couple, and then we'll move on. First, one important thing is to be able to translate a statement like this, a sentence, into a chemical equation. So during respiration by plants and animals, a carbohydrate, in this case glucose, reacts with oxygen to produce water and carbon dioxide. So what are the reactants? What am I putting on the left?
Water and
No, the others. Those are going to be the products, right?
C60.
And the key words in these kinds of things are things like produce, reacts with, and that kind of tells you what's on one side and what's on the other. So in this case, we've got glucose C6H12O6 reacts with oxygen to produce water and carbon dioxide. All right, is that balanced?
no.
Probably not. We have to balance the carbon, the hydrogen, and the oxygen in this, since that's what's here. None of them are in balance right now. And one way you might want to do it, if we're really going through it, is first just add up what you have of each. So on this side, we have 6 carbons total, 12 hydrogens, and 8 oxygens. And on this side, we have 1 carbon, 2 hydrogen, 3 oxygen. So clearly a bit out of whack. Many of these will be very easy. You'll just look at it and say, oh, there's got to be a 2 here and a 2 here, and we're done. But some of them are going to take a little bit more work. If you want to do it in a systematic way, meaning step by step, where you always do it the same way, what I recommend is always do the elements first that are in the fewest molecules. For instance, in this case, carbon is only in 1 molecule on the left and 1 on the right. Hydrogen's on 1 on the left, 1 on the right. But oxygen is in 2 on the left and 2 on the right. So that means that carbon and hydrogen are going to be easier to balance first. If you try to balance the oxygen, you don't really know where to put the numbers. So anything that's in multiple molecules, leave that till later, or till the end. So you want to start with carbons or hydrogens this time? Carbon, fine. So to do that, we might say, okay, there's 6 over here, 1 over here. So I got to add some more and have 6 total over there. Now I've got 6 again. So one thing you might want to do, as you're still learning this, is each step mark what's changed. So now we have 6 carbons, and we've changed the amount of oxygen also. We now have 13 oxygen. So let's balance hydrogen next. We have 12 over here and 2 over here. So what do we have to put in front of the water? 6. Okay, that'll give us those 12 hydrogen, but that also changes our oxygen again. So we now have 18, right? So now we've got 8 on the left and 18 on the right. So how do we change this one on the left to get more oxygen? Right, okay. So we're going to put a 6 here. Now we've got 6 from these oxygen, 12 here. So now that's 18 oxygen. Now everything works out. Also, we should note here, if we can, we don't always know, but we should note the states of these as well. So the glucose in this case is probably aqueous in a plant, right? The oxygen is a gas from the air, although it ultimately ends up being aqueous when it actually reacts, so either way is okay there. Water is a pure liquid, and carbon dioxide is produced as a gas.
Do we also write that?
What?
Do we also mark that?
If you can.
I know on
If you can.
master chemistry,
Yeah, mastering chemistry you certainly do. It's always a good idea. In your labs, you certainly should for tomorrow. All right, let's try another one. Methane is destroyed by reaction with hydroxyl radical to produce a methyl radical and water. So if the methane is destroyed, that's probably a reactant, right? And methane, in this case, it's not specified, but I'll tell you, it's a gas. And that's destroyed by a hydroxyl radical. Who knows where this is happening? In the atmosphere, maybe, or who knows? Let's say this is also a gas. Let's say everything's a gas in this case. And this produces a methyl radical and water.
Why
No, I mean, in some cases, yes, but it'll be a lot clearer than this. This is just a guess for all of us. So what do you think? Is that balanced?
Yeah.
It is, so we're done, right? Okay. Let me see if we can skip a couple here and get to a good one. So this is interesting. Here's a good math puzzle for you. Let's do one more and then we'll do the math puzzle. The tricky one is number 5. Let's do... Some of these are not that tricky. Okay, let's try this. Number 6. Denitrification in soils and oceans occurs when the nitrate ion is reduced to nitrous oxide by anaerobic bacteria in the presence of water. Oxygen gas and the hydroxide ion are also produced. So first I'm going to draw that because that's easy. I know oxygen gas and hydroxide ion. Whoops, not a gas. It's going to be in solution. Ions can generally always be assumed to be in solution. So those are produced. And what else is produced? Well, the nitrate ion is reduced to nitrous oxide. So the nitrate ion, what's the formula for nitrous oxide? You know that one? It's N2O. Give myself a little more space here. And that's a gas. And what else is happening? The nitrate ion is reduced to nitrous oxide by anaerobic bacteria in the presence of water. So there's going to be some water here too. Okay, see if you can balance this one, and then we'll talk about it. Okay, so what do you balance first? Maybe either the nitrogen or the hydrogen, because those are the ones that only appear in one molecule on each side. So to balance the nitrogen, we've got 2 over here. We've got to add 2 here. All right, now let's balance the hydrogen. You got 2 over here. You need 2 over here, right? And now let's balance the oxygen. So on this side, we have 7. And on this side, right now, we have 1, 2, 3, 4, 5, right? So if we have 2 more, then we should have 7, right? And it's balanced? All right. So here's an example of one that you definitely would get in trouble if you tried to balance oxygen before hydrogen. Right? Because you'd end up putting numbers places that wouldn't work out and it would get all screwed up. All right, let's see how well we really understand this stuff now. This is a bit of a challenging one. During combustion of fossil fuels, this is number 5, hydrocarbons react with oxygen to produce carbon dioxide and water. Now all carbons, or all hydrocarbons, saturated hydrocarbons they're called, have this type of formula, CnHn plus 2, 2n plus 2. So you have like, when n is 1, you have CH4. N is 2, you have C2H6. N is 3, you have C3H8. Those are known as methane, ethane, propane, all of these combustible hydrocarbons, fossil fuels. And they all have this type of formula. So if we can balance the equation with a variable like that, with the series, then we have sort of a general tool to balance any of these. So let's see if we can do that. The basic reaction that is going to look like this, CnH2n plus 2, reacts with oxygen to produce carbon dioxide and water. So we're going to balance these the same way. What element do you want to balance first? The carbon. So how do you balance the carbons here? What? How? Right, so if we start with n carbons, then we need N carbon dioxides coming out. All right, what should we balance next? All right. Let's look at the hydrogens first, because the oxygen is in two different places potentially, right? So the hydrogen is 2N plus 2. We're putting in 2N plus 2. So how do you balance H2 with H2N plus 2? Well, let's think about it. Basically what we're saying is, right, we're saying what number times 2, right, because H2. So what number times 2 equals 2N plus 2? N plus 1, right? So this is going to be N plus 1. And then we check it. How many hydrogens are on this side? N plus 1 times 2, which is 2N plus 2. How many hydrogens are on this side? 2N plus 2. So it still works. Okay. Now is the tricky part. I'll give you a couple minutes to think about this. How do you balance the oxygens now? So think about it. Maybe try to set up a similar equation to this to figure out how many oxygens do you have to have here to balance out with these. So let's set up the equation and see how it works. So what we're saying is, what number here times 2 equals all the oxygen on this side? So X times 2 again equals all the oxygen on this side. And all the oxygen on this side is 2 times N for these, right? And N plus 1 on over here. Which is, you can split that up and call it 3N plus 1. So that means that X equals 3N plus 1 over 2. So you're going to have 3N plus 1 over 2 oxygens. And that works, because if you multiply 2 times here, you have 3N plus 1 O's. And here you have 2N and N plus 1, so there's 3N plus 1 over there as well. So the lesson of this is certainly a tricky problem, but the lesson of this is for equations that potentially get very, very difficult to balance, you can set up some algebra and then actually solve for what you need. So if it's complicated, you don't know how many oxygens or whatever you need, you can set up the algebra and do it this way. Okay. Just like with other stuff, yep. Just like with other stuff, this comes with practice. So let's do a tricky one and see what that might look like. Well, that was a tricky one, yeah. I mean a tricky one with numbers, with regular numbers. So try this up in. You did it? Good job. That is the nice thing about these. You can always sort of get it if you play around with it for a while, because you always know if you're wrong, and if you're wrong, you change things. You can always keep adding them up. So let's look at this. We've got C3H5N3O9. Gives you carbon dioxide, water, nitrogen, and oxygen. All right. So which one did you try to balance first? Well, if you tried to balance carbon first, that's fine. But here's why I actually wouldn't go that way in this case. Any of the other ones, again, I would leave oxygen till the end because of it's present in multiple molecules. But hydrogen or nitrogen have odd numbers on one side and even numbers on the other side. And what that tells you right away is that you're going to have more than just one of the thing on the left. Because you can't turn an odd number or an odd number into an even number unless you have at least two of those to start with. So I might say, all right, let's balance nitrogen first. And that's going to give me, I'm going to need 2 of these and 3 of these to get that balanced. Right? And then what about hydrogen? Then we'll need 5 hydrogen. And then what about carbon? We'll need 6 of these, right? Because we've got 6. All right, so now let's check our oxygen. On this side we have 18. And here we have 12, 5, and 2, which is 19. Well, that's a problem, right? Because we've got 18 here, 19 here. We can't just add one more oxygen atom on this side. So what do? We have to increase it. Now, here's the trick for that. We know we're going to need more than just 2 here. We're not going to try to find a common multiple of 18 and 19. That's going to be a huge number, although that is a way to do it, and then you could reduce it down later. That's fine. But here's the thing. We know we need to increase this. We can increase it by 1 and go to 3. That's going to cause another problem. What's that problem going to cause? What's that going to cause? Yeah, it's going to give us that odd even thing again. We know we have to have an even number here because N2 and H2 are in pairs over here. So I would suggest going to the next highest even number, which in this case is 4, right? Okay, so let's erase all these numbers now and redo that with 4. So we've got, we'll do it in the same order. That's 12 nitrogens here, so that's got to be 6. 20 hydrogens, so 10. And 12 carbons. And then let's check the oxygen. 4 times 9 is 36. Then we've got 24, 10, and 2, which is 36. All right, so it works. Okay? So noticing those kind of things that can cause problems can help you to do this quickly. Another way you can do it is just to keep increasing that number one by one. If you didn't think about the even odd thing, that's fine. Just keep increasing it. Does 2 work? Doesn't balance out. Does 3 work? You'll find it doesn't balance out. Then you get to 4, and finally it would work. So you can. There's quite a bit of trial and error involved in these, and the more difficult they are, it's just the more time they take. But there shouldn't be any reaction that you just can't do. It's just going to take you more time to try more and more numbers and multiply bigger and bigger numbers. Okay, so questions about balancing equations? Everybody good? Just do your practice these, do a million of them, whatever in the book, and I'm sure you'll be fine. All right, types of reactions. These are what we're going to do tomorrow in lab. So let's talk about them. 3 basic types that we're going to discuss now. Precipitation, acid-base, and oxidation reduction. And we're going to look at how to identify them, how to put them in those categories, and then how to write the equations. And the point of all of this, actually, is to start being able to predict what will happen when you put things together. That's really a big goal of all of chemistry. Can we actually predict, can we figure out what's going to happen when we put these things together before we actually try it? There's safety implications there. There's all kinds of stuff there. You want to know what happens when you mix chemicals. And ideally, you want to know that before you actually try it. Sometimes you can't. That's why we do experiments. But a lot of times you can. So I'll talk about the categories, and then we'll figure out how to get various reactions into those categories. And if we don't finish this, we'll keep talking about it tomorrow in lab. So that's fine. All right. So sometimes you mix some aqueous solutions and a solid forms. How that looks usually is just that it turns cloudy. A solution turns from clear, that you can see through it, to cloudy, where you can't see through it. Sometimes you actually see the formation of like a solid that falls to the bottom, but often it just gets cloudy because the pieces are very small. Here are some examples of that. You put in silver nitrate with sodium chloride, you form silver chloride and sodium nitrate. Silver chloride is a solid. It's not soluble in water, it precipitates out. Same thing with calcium hydroxide and carbonic acid. Zinc sulfate, sodium phosphate, forms zinc phosphate, a solid. We'll be doing this reaction next week, or the week after the exam. So then let's try like these. So this is kind of how, this is what we're trying to do here. Is now what happens if we see something like this? What are we going to make? Why does this happen? What is happening? Well, let's go step by step. You may know this already. Let's go step by step. When you dissolve something in water, speaking of that something, what is the name of that? Potassium chromate, right. So when potassium chromate is dissolved in water, the first thing that happens, you've got solid potassium chromate, an ionic solid, you put it in water, it dissociates, meaning that this K2CrO4 solid becomes an aqueous potassium ion and an aqueous chromate ion. Is that balanced? No, we need to have two, which makes sense because there were two of these that dissociated, so now you've got two of these and one of these. All right, so now these individual ions are floating around in solution. Same thing with barium nitrate. Barium nitrate dissociates, whoops, that's a solid, dissociates in water to form barium ions and nitrate ions. Two of them. So what you sort of have in the solution now is a scramble of all the different ions. They're all there. And even though we write this reaction as these two things coming together, because that helps us in weighing out our materials and so forth, the actual better picture of what's happening is to say all of these ions are coming together. So potassium ions and chromate ions are mixing with barium ions and nitrate ions. All of these aqueous. To form products. Now, if this is a precipitation reaction, which it is, what we need to know is how do these ions possibly combine to form something that is insoluble in water? Insoluble in water. So any predictions?
The sign, the plus and minus that are equal to each other combine.
The plus and minus that are equal to each other would combine. So you get potassium nitrate and barium chromate. Okay, it's a good prediction. Do you think both of those will be insoluble or just one? Any ideas? Well, I mean, there's other crazy stuff that could happen too, right? You could get barium chromate nitrate or something where the ions go together. These are really unlikely. But usually, you guys are absolutely right. The solid then contains equal charges and stuff comes together to balance out one cation and one anion type. So here are all the possibilities. You could have just made the stuff that you started with. Of course, that's still aqueous, so basically nothing would happen. Or you make the new things that you all talked about, potassium nitrate and barium chromate. So how do you know if anything is actually going to happen? Well, you need to know if any of these are insoluble in water. And to do that, you look at a table like this. And I'm sure you're excited about this. You won't actually need to look at this table because you'll have it memorized, because this is something that you should know. So there are certain, and it's not as tricky as it looks. There are some generalities here, but there are some compounds that are generally soluble or generally insoluble, and we can look at these and figure this out. So generally soluble ones are in the top. That means in most cases those things are soluble. And generally insoluble ones in the bottom. So hydroxides, sulfides, carbonates, phosphates. And then of course there's always exceptions. All right. So the best thing to do here is to split this up into kind of categories, because let's look at this. Here are your generally insoluble ones: hydroxide, sulfide, carbonate, phosphate. Look at what the exceptions are. The exceptions are basically those first two rows plus ammonium. The first two columns, sorry. okay? More or less. So that gives you a reasonably, or the bottoms of those, the second one. That gives you a reasonable general thing to memorize instead of at each individual one. The ones up there are no exceptions to lithium, sodium, potassium, ammonium compounds being soluble, nitrate, acetate compounds being soluble. And then for the halides and for sulfate, you're looking at some of the heavier metals and some of the alkaline earth metals. Based on this chart then, which of those compounds above would you expect to be insoluble? And I'll give you a hint, it's not on this chart. So you have to kind of make a guess based on what you do see on this chart. What do you think? If one of these has to be insoluble, I'll write it down here so you can see it. Either potassium nitrate or barium chromate. If one of those has to be insoluble, which one's it going to be? Why the barium? Yeah, everything from potassium and everything from nitrate is always soluble. Those are very, very soluble. So even though the other one's not on the chart, we know there are some barium compounds that are insoluble, so we'll go with that one. And in fact, that is the case for this one. Okay, so let's use that table now to look at these reactions and try to figure out what will happen. And when I say what will happen, I mean, will anything happen? Will a precipitate be formed? If so, what will that precipitate be? So let's look at the first one. Potassium nitrate and barium chloride. Do you think a precipitate will be formed? What do you think that precipitate will be if it's formed? You don't have to just guess. You can flip back to the table or something if you've got it. Let's look at it. So what are we going to look at? We know potassium nitrate and barium chloride are already aqueous, so we don't have to look at those. What we care about are the displacement products, the barium nitrate and the calcium or potassium chloride, right? Right. So all nitrates are soluble. So the barium nitrate will be soluble. And chlorides are soluble except for these ions, and we don't have that ion. So potassium chloride is also soluble. So what happens when these are mixed? Nothing. There's no reaction. Okay. And that's an important conclusion to a lot of these things. In fact, most things that you mix, you won't get a reaction. And things like for your exam or for lab tomorrow, that will certainly be a reasonable response. It'll say what happens to this reaction. Maybe nothing happens. Maybe one of these precipitates. Maybe the other one precipitates. It's kind of a quick multiple choice question, but no reaction is usually always one of the choices. So that's always a possibility. Okay. And what about this next one then? Sodium sulfate and lead nitrate. Yeah.
The sodium nitrate would dissolve.
Okay.
And then the lead sulfate would precipitate.
Lead sulfate would precipitate. Sounds good. Well, let's go up here and check. Sulfates are generally soluble unless paired with lead, in which case they're insoluble. So yep, probably what you would get here is a lead sulfate solid as a precipitate. What about potassium hydroxide and iron nitrate? Iron 3 nitrate. Close. It would be the iron hydroxide. Hydroxides are generally insoluble, except for the couple exceptions given here, and we don't have one of those. Whoops. We don't have one of those. We have iron 3. So we would expect here to get one's blowing up. We'd get an iron 3 hydroxide solid. Okay. So there's a couple ways we can write these, and you'll hear this terminology tomorrow. There's also some of this stuff in part of the pre-lab. You have a molecular equation, which is what we're used to seeing. This reacts with this, forms this and this. Then we also have the complete ionic equation, which is what we just did before, where we write out all the ions that are participating. But note what you don't break up is things that are solids. So you break up all the aqueous ions, anything floating around. That gives us a better picture of what's actually in solution. And then we can split that even further down, or reduce that down into the net ionic equation. Only the ions that are participating in a reaction are in the net ionic equation. And how you come up with that is any ion that's on both sides gets canceled out. So these potassiums aren't reacting, they're not doing anything, they're floating around in solution. So they're called spectator ions, and they're not involved in the reaction. We can cancel them off, same with nitrate. And the only reaction that's really happening is barium ions and chromate ions are reacting to form barium chromate solids. And that's a precipitation reaction. So part of your post-lab tomorrow, or pre-lab if you want to do it before, I don't care, will be to write the net ionic equations for each of the reactions that you do that result in a product. So it'll be good to look at some of these practice exercises. We don't have time today. But we'll talk about this more tomorrow.